In this slide, we're actually seeing what some of the rooms and some of the houses look like in chemistry, when you put electrons around orbitals. And this is pretty cool. Now, I'm going to circle here some of the subshell / houses. And every one of these kind of tan combinations, these are all subshells. And notice how, remember I said how a subshell is like a house. Well, some houses have just one room. So this big purple thing, that's a room. That's an orbital in the 3s subshell. On the other hand, right next door is a little bit fancier house. This house has 1, 2, 3 rooms in it, 3 orbitals in the 3p subshell. So if this was a house, this would be a 3-room house. The 3s house, on the other hand, would be a 1-room house. And on the far right over there, these are the 3D house, if you will. There are 5 rooms, 5 pictures right there. Those are the 5 orbitals in the 3D house. So each of those things I just circled, plus the ones below it, like 2s here and 1s, etc., those are the subshells, all right? And some subshells have just one orbital. The left-hand side is an example of that. Some of the subshells, like the 2p and the 3p, have 3 orbitals, and some, like the 3d, have 5, and there are other kinds as well. So these literally are the pictures of the room's orbitals, if it's an individual, or the subshells. If you combined all the 3p little orbitals, that would be the 3p subshell, that house, and that's pretty cool. Now, to talk about all of these, you can see there's like a number and a letter. And this kind of system is called the NL notation. The number that's in front is the N value. So for like 3s, that means N equals 3. The L value, as we saw in the last example, also has a number associated with it. But if you put a 0 or a 1, it might look like 30 and 31. It would be hard to tell. So people have developed this little acronym: stupid people drink freaking gas. Don't drink gasoline, kids. But anyway, each of those letters is associated with an L value. So for S, stupid, all right, that's the S, that means L equals 0. So for 3S, when you see 3S, that means N equals 3, L equals 0. On the other hand, this one right here, these are the 2Ps. So if you wanted to know 2P, the 2 is the N equals 2, and P, the people of this little acronym, means L equals 1. So it's really important that you know how to find the N and the L value. The N is easy, it's just the number. The letter, you have to figure out what it stands for. And there's different versions of this. Stupid people drink freaking gas. Stupid people drive freaking gas hogs. If you want to go H5, which is down below. All of these are good, but you do need to know what number is associated with the letters. Make sure you know / memorize that. Here's a question where it says a certain orbital N equals 3, L equals 1, M sub L equals -1. What type of orbital is this? Good. So this is the NL notation. N of 3 means the first number will be 3, so it definitely won't be answer D. And what we have to do is figure out what L equals 1 means. So if you go over here to this little diagram, L equals 1 is P. This should be a 3P, or answer C would be right. If it was 3S, you would have L equals 0. If it was 3D, you would have L equals 2. So you can hopefully quickly interpret what the NL notation means in terms of N numbers and L numbers. When N equals 1, L, which is only from 0 up to N minus 1, L can only be 0. And if L is 0, M sub L, which goes minus L to plus L, can only be 0. What this means is that in the N equals 1 shell, there is only one subshell. So N equals 1 is where I got the N equals 1 shell. There's only one value of L. That means there's only one subshell. So L equals 0 doesn't mean there's no zeros. All right, that's a legit value of L, and that means there's one subshell. And because there's one allowed m sub l value, and again, m sub l of 0 doesn't mean there's not one, that's one allowed value. M sub l of 0 means single orbital. So you can quickly tell that in the n equals 1 street, there's one house, and that one house has one room. In chemistry, the n equals 1 shell has one subshell. That's an S subshell, by the way, from the SPDF thing. And that one S subshell has one room, and m sub l equals 0. And this is how people figure this out. This is the 1S subshell. S comes from the fact that S's kind of look spherical, like a big sphere. And people that know more German than I do say that sphere is sphere, whatever, and spherical spherisch. Okay, and again, I'm the worst. I can't even do English, let's be honest. But anyway, that's supposedly where the S comes from. So all of the S's, 1S, 2S, 3S, as we're going to see, are basically spheres. If you look back at that last picture on the far left, all of them were basically spheres. Now, if you've seen in chemistry electron filling orders like 1s2, 2s2, 2p6, that kind of thing, this is the 1s. And you now see that it came from quantum mechanics. 1s means n equals 1, l equals 0. You know that those are legit rules. We're going into this a little deeper than you may have done before, but it's all stuff you can do, and that's kind of cool. Here's some pictures that kind of show a little bit more what's happening. Now, s orbitals always have L equals 0. SPDF means L equals 0. And so s orbitals are always spherical, okay? And so if you look at these pictures right here, this is like a side view of what it looks like. And you can see that at a certain point, it just gives out, all right? That's basically a sphere. And you can also notice maybe that right here it says R90. That's a probability that the electron will be inside there 90% of the time. And usually that's pretty good. I talked earlier, a long time ago it seems like now, about nodes. And nodes are places where there's no electron density or no wave. And we start seeing spherical nodes when the orbitals get bigger and bigger. A spherical node is like a ball within a ball. And that ball within a ball is where there's no electrons. And spherical nodes, you can calculate them using n minus L minus 1. So this video that's showing right here, there's like color bands, but inside the bands, there's some black lines. Those black lines are the spherical nodes. If you have a 6s orbital and you want to know how many spherical nodes there are, you better know the n and l values. So 6 is the n, that's the 6 right there. S is L equals 0, that's that one right there, and n minus L minus 1, this thing has 5 spherical nodes. So we're going to talk a lot about types of nodes when it comes to these crazy subshells and orbitals. And n minus L minus 1 is the way to find the number of spherical nodes, and we'll come back to that later. This is the 1s orbital, all right? It's in the 1s subshell. The 1s subshell has just one orbital, and you can see in the middle there, that little kind of shiny stuff, that's in the middle of that diagram. That's the actual 1s electron, all right? And really, it's a shimmering sphere because it represents 90% of the electron, blah, blah, blah. Speaking of probability, psi star is the way they find the probability, all right? And you can tell there that if you take that, that's how they find these 90% confidence kind of things. Now, no spherical nodes. N minus L minus 1 would be 1 minus 0 minus 1, 0 spherical nodes, nothing in the 1s orbital. Notice how small the 1s orbital is. The 2s orbital is bigger. The n value is proportional to the size, more or less. So 2s is bigger than 1s, 3s is bigger than 2s, etc., etc. If you look in this two-dimensional representation on the right-hand side, there's like a white circle in the middle of a dark black circle and the other black stuff around it. That's one of the spherical nodes, and it's represented right there in this graph. 2s has one spherical node. It's like a node with a sphere within a sphere, and on that sphere you have no electron density. So n minus l minus 1, n is 2, l is 0, so 2 minus 0 minus 1, one spherical node, and that's what you're seeing there in the middle or in the graph. So it's kind of interesting. So again, 2s is bigger than 1s, but again, it's basically a sphere, one spherical node inside there. That's kind of important. 3s is bigger yet, all right? It's even bigger than 2s and is getting bigger. You went from 2 to 3. There's two spherical nodes, which you can see in those little graphs there on the right. My little animation in the lower left is kind of mesmerizing, but there are actually two black line kind of spheres in there, and those represent the spherical nodes. So it's kind of cool to see. 4s, of course, would be bigger yet. 5s would be bigger, and every time you raise an n, you have one more spherical node. We talked about n equals 1, what happens then. Let's now talk about n equals 2. Now when n equals 2, you have two possible values for L. Remember, L goes from 0 up to n minus 1. So that means that allowed values of L will be 0 and 2 minus 1, 1. So when n equals 2, you've got two L values. Now let's break that down into some language. The n equals 2 shell has two subshells, the L equals 0 subshell and the L equals 1 subshell. The n equals 2 street has two houses on it, an L equals 0 house and an L equals 1 house. This is kind of how this stuff all begins to play around. Now, we've actually already seen the L equals 0 part. We'll talk about that. But there are two types of subshells, two types of orbitals, and each subshell has its own type of orbital. The L equals 0, which means m sub L equals 0. This is the 2s subshell I showed you a picture of. So remember that if L equals 0, m sub L goes from negative L to positive L, so that's only L equals 0. If L equals 0, that's an S. So this is going to be the 2s subshell, and that's one we saw a picture of earlier. No problem. But the other possibility is when L equals 1. When L equals 1, it's a different game. M sub L goes from negative L to positive L. So if L is 1, that means M sub L is going to be negative 1, 0, and plus 1. Those are the three allowed M sub L values. And so what we would say is there's going to be three orbitals because of the three allowed M sub L values. And if we're going to designate this, still at n equals 2, but now L is 1, that's going to be a 2p subshell. So this is the first time now that we've seen a 2p subshell. There was not a 1p subshell, all right? There was only the 1s. But when it comes to n equals 2, we've got a 2s and a 2p. And the 2p has three orbitals in it. You could think about it that the 2p house has three rooms inside it, while the 2s house had just one room. So the 2p subshell is a little bit more elaborate, if you will, than the 2s. Planar nodes are another type of wave phenomena that occur when you have different combinations of orbitals. And planar nodes, we're going to see, are equal to L. So when L equals 1, you can see there's like this line, this sheet of glass that goes down the middle that separates the two of them. That's a planar node. Planar nodes equal L, and all p orbitals have a planar node that goes right through the nucleus. Here's a better representation of those planar nodes. You're going to see that there were three m sub L values, and you can think about the m sub L's. This isn't quite correct, but it works for this conversation, okay? The m sub L values, negative 1, 0, and plus 1, all right? And so those represent the three orbitals in each of those those m sub l values. And that sheet of glass will literally go between the orbitals. Notice that all of these look kind of like a figure 8, all right? And so the plane of glass goes right through the middle. So in this case, you can see it's in the first one, it's in the YZ node, and the second one, the XZ, et cetera, et cetera. They all have a planar node. Also importantly is that they're all at 90 degrees. So the X, Y, and Z is no accident. It's considered to be an X-axis, a Y-axis, and a Z-axis kind of plane. So you can see that if it's X, then that figure 8 is right along the X-axis. And if it's Y, it's right along the Y-axis. And of course, the Z up and down, traditionally up and down is the Z-axis. So you're kind of hopefully seeing how this stuff all works out. So again, s orbitals are in the s subshell, and there's only one of them. But if you do have a p subshell, then there are 3 p orbitals, and one you can think about as x, y, and z. Kind of cool. 2px is just a p orbital aligned along the x-axis. So you can see in the picture right here, this is the x-axis, and here's that figure 8. Now notice there's a planar node. It separates the two nodes, the two lobes of the p orbital. Pretty cool. I'm having it rotate there because I guess it looks kind of pretty. Now 2py and 2pz would be very similar. If it was 2py, it would be along this axis. And you can imagine if this was a three-dimensional graph, there would be a z-axis right here, and that would be along the z-axis. But they're all basically the same. They're just at 90 degrees from each other. 3px is bigger than 2px, just like 2s was bigger than 1s, but 3s was bigger than 2s. So again, 3px means that most of the interaction is going to be along the x-axis, and it looks more or less like the figure 8. But we're running into, first of all, the planar nodes. Planar nodes always equals L, but remember that spherical nodes equal n minus L minus 1. So spherical nodes for 3p would be 3 minus 1 minus 1, one spherical node. And oh my goodness, so you've got this kind of thing going around here. That's the spherical node as well. So using NL, you can find spherical nodes. Using the L values, you can find the planar nodes. And again, 3py would be similar. It would just be along the y-axis, and 3pz would be similar, but along the z-axis. How many total nodes in a 4p orbital? And you have those possibilities right there. So before we do that, let's figure out what n and l are for the 4p. So 4 is the n, all right? The number literally is the n value, so that's good to go. P, it goes SPDF for 0, 1, 2, 3, etc. P is the second one, so P means that L equals 1. Now, when it comes to total nodes, there are planar and there are spherical. And planar nodes just equal L. So if L equals 1, the 4p orbital would have one planar node. But there's also, remember, spherical, and spherical n minus L minus 1. So here, n is 4, L is 1. We subtract 1 on top of that, n minus L minus 1, 2 spherical nodes. So there's one planar node, 2 spherical nodes. There's a total of 3 nodes total, sorry. Planar nodes, as I said, equals L. Spherical nodes, n minus L minus 1. So there's one planar node, there's 2 spherical nodes, add those up, 3 total nodes. So this is a good question because it forces you to find, of course, the n and l values from a certain NL designation, and then you can find planar nodes and spherical nodes, put them together, good to go. D orbitals are when you run into L equals 2. And we haven't seen D orbitals when n was 1 or 2. Remember, n equals 1 had just one s. N equals 2 had 2s and 2p. But we haven't seen D at all yet. So when n equals 3, what are the values of L? L always goes from 0 up to n minus 1. So if n is 3, that means L is going to be 0, 1, and 2. Those are all allowed L values. Each one of those is a subshell. There's going to be 3 subshells in the n equals 3 shell. When L equals 0, M sub L is 0. L of 0 is an S. This is the 3S subshell, and it's similar to 1S and 2S, just bigger with more spherical nodes. It has a single orbital. When L equals 1, M sub L goes from negative L to positive L, negative 1, 0, and plus 1. These are the 3p orbitals. So the 3p subshell has 3 orbitals, x, y, and z is the way you can think about it and stuff. No problem. And 3p bigger than 2p, but otherwise pretty similar. But the new player now, when you get to n equals 3, is L equals 2. If L equals 2, M sub L goes from negative L to positive L. So that means negative 2, negative 1, 0, plus 1, and plus 2. Those are the 5 allowed M sub L values. That means there's going to be 5 orbitals in the 3D subshell. So again, you can think about the 3D subshell as like a type of a house. And this type of house, subshell, has 5 rooms, 5 orbitals. So it's a little bit fancier kind of house than we've looked at before. The L equals 0S house had just 1 room, 1 orbital. The L equals 1P house had 3 rooms, 3 orbitals, but woohoo, this L equals 2 house has 5 rooms, 5 orbitals, even cooler. So d orbitals, when L equals 2, all right, are kind of cool. S orbitals have no planar nodes, and so they're spherical. The p's had 1 planar node. They're dumbbells, figure 8 shaped, infinity, whatever you want to call them. D orbitals, you can extend it out too. Now, d orbitals are going to have 2 planar nodes. L equals 2 means 2 planar nodes. And what most of these look like are like 2 big p orbitals. Like the darker purple one there, that's like 1p, and the other kind of lighter red one, that's the second p. And you can have literally 2 sheets of glass, 2 planar nodes, kind of bisecting them like that. So most of the d orbitals look kind of like 2 figure 8s, 2 of the p orbitals squished together, but they will have 2 planar nodes one way or the other. Remember, planar nodes equal L, and spherical nodes n minus L minus 1. So this is an example, a picture of the dxy orbital. You can see that there are 2 sheets of glass going through it. That's because if you have L equals 2, you will have 2 planar nodes, 2 pieces of glass, and you can cut them through those figure 8s more or less. Here are the px, py, and pz's. Those p's have 1 planar node, L equals 1, but the d's will have 2 of them. All right, it depends which one you look at, but they're basically separating the nodes together. So instead of having just one thing of it, it's like you're combining 2 of them to have 2 of them. I don't know if that works for you, but it works for me anyway. This is the 3D XY orbital, all right? And the 3D XY, if you look at the picture on the left, one of them is kind of between the X and the Y, and the other one is on the opposite side. But again, 2 spherical, thanks for playing, 2 planar nodes are inside there, all right? And you can see it's shimmering and stuff like that. N minus L minus 1 is the way to find spherical nodes. 3 minus 2 minus 1, these don't have any spherical nodes. They will have planar nodes. L equals 2 means 2 planar nodes, but they don't have any spherical nodes. This one is the 3DXZ, all right? So you can see again how you have kind of like 2 of these figure 8s, and they're between the X and the Z axes and stuff like that. But again, they look very similar, just different axes. This is 3D YZ. So again, those figure lobe things are kind of between the Y and the Z, and they rotate around, looking pretty cool. The 3D Z squared, I always call the donut orbital, and that's not really accurate, but it is kind of fun to think about. These guys have a harder spherical or planar node, to see, but you can see here in this two-dimensional picture, there are literally two of them kind of bisecting it and stuff inside, which is pretty cool. So this is the 3D Z squared orbital, and then there's also the 3D X squared minus Y squared, and this orbital is right in the X and the Y plane. So you can see this one's right along that axis, and this one is right along that axis. So pretty similar. And again, 4 of the 5 of them look kind of like 2p orbitals squished together. The donut shaped is a little bit different. Here's an example I want to do with you. I want to go through the n equals 3 shell, and we're going to talk about how to get all these values, and I encourage you to, if you want, you can pause this video, see how many of these little pieces you can fill in, and then we'll go through and fill them all out for you. So then n equals 3, L values, L goes from 0 up to n minus 1. So if n equals 3, that means L is going to be 0, 1, and 2. Those are the 3 subshells when n equals 3. And those are going to have a letter we'll see associated with them as well. But again, when L goes from 0 up to n minus 1, 0, 1, and 2. Now, each one of those L values has a letter, and it goes S, P, D, F, G, H. After that, S, P, D, F are honestly the most important ones. So L equals 0 is S, L equals 1 is P, L equals 2 is D, etc., etc. So for NL notation, which is n number first followed by the letter L, you would have 3S, 3P, and 3D. That would be the way to designate the different subshells from each other. Now, m sub L has to do with the number of orbitals, but we're just looking for the raw numbers here of m sub L. M sub L values go from negative L to positive L. So for example, for the 3s, L is 0, negative 0 to positive 0, there's only going to be an m sub L of 0 for that one. But when it comes to 3p, L of 1, negative 1 to positive 1, the m sub L values will be negative 1, 0, 1, plus 1. And for L equals 2 over there, you'd have everything from negative 2 to positive 2. So these are the m sub L numbers. And you can see how it goes 1 m sub L value to 3 m sub L values to 5 m sub L values. Quantum mechanics is filled with patterns. So just FYI, you're going to see a lot of them, and this is one of them. Now, each one of those m sub L values is an orbital, even 0. 0 is legit. That's a legit value. So if you have m sub L of 0, that's going to be 1 orbital. If you have m sub L negative 1, 0, and plus 1, those are 3 orbitals. And of course, the last one would be 5 orbitals. So there's lots of different ways to do these kind of things. The total number of orbitals, if you count 1 plus 3 plus 5, you'll see that it's 9. A quick way to do this is that if you have the n value, n squared is another way to find the total number of orbitals. So n equals 3 is what we started with, 3 squared, 9 orbitals total. But now you can see kind of like where they all come from, and that's kind of a cool thing. Some people like using the train track model to represent this, and that's fine too. Up here on the top in red, these are the n values. So there's n equals 1, n equals 2, n equals 3. And like we saw, if n equals 1, there's only L of 0, which is the S, and the L equals 0 has just one m sub L value, one orbital. So that's the 1s orbital in the 1s subshell. On the other hand, when you get to n equals 2, then L values are 0 and 1. They always go up to n minus 1. L of 0 is just an S. That's the 2s. But when L is 1, then m sub L, negative 1, 0, plus 1, those are the 2p orbitals. And then over here, you can do the same kind of thing. This would be 3s. these would be the 3p, and these here would be the 3d. And you can do this for all of them. It works really well. Just make sure you figure out a way to make this all work in your head. There are f orbitals too, and we're not going to spend as much time on them, but when you get to n equals 4, you've got L values going from 0 up to n minus 1, so that means 0, 1, 2, and 3. So there are 4 subshells, 1, 2, 3, 4 values of L. So that means 4 subshells in the n equals 4 shell. The first one, when L equals 0, m sub L equals 0, that's just the 4s subshell, and there's a single orbital. When L equals 1, m sub L goes from -1 to +1, so there's 3 values of m sub L. This is the 4p subshell with, again, like we've seen earlier, 3 orbitals inside it. L equals 2 at this point means m sub L goes from -2 to +2, 5 m sub L values, 5 orbitals in the 4d subshell, and the new player on the block, L equals 3. If L equals 3, m sub L -3 to +3, those are 7 possible values. This is the 4f subshell with 7 orbitals. Now, a lot of times they don't even show pictures of these, but I think it's kind of cool. These are the best pictures I could find of the different f orbitals, and they're pretty cool looking. They more or less look like, depends on the orbital and stuff like that, but more or less there's like, oops, let me draw here. There's like 1 of the p orbitals, there's 2 of the p orbitals. They more or less look like 3 p orbitals squished together. Some of them have the donuts and stuff. There's some really cool kind of chemistry going on, but again, we're not going to focus so much on the orbitals, but it is kind of fun to see what they look like. And if you have to make a guess, 3 of those p orbitals squished together would be a good thing. Now, L equals 3 for these. They're all going to have 3 planar nodes too, which is kind of neat.